the another two orbits, and then we will exercise those problems. So we have two orbits. One is the circular. And parabolic. Okay, so for circular orbits, so here is the only quick summaries from the properties we've been talking about. So we know the mechanical energy that is true for all kinds of the orbits. So v squared divided by 2 minus mu divided by r. And say, for example, the circular orbit of radius a, r equal to a. Today we have one handout over there, so pick it up. So under these situations, and you can see basically this one can be described as when we plug in r equal to a, so that is v squared over 2 minus mu over a. Okay? So simply by introducing r equal to a. On the other side, we know in general this mechanical energy also can be described by minus mu divided by 2a. What is 2a? A is the semi-major axis. So basically that is for circular, that is a. So under these situations, we simply relate the two equations together. So then we have is v squared over 2 equal to mu divided by 2a. Okay, so therefore here we have the v. Velocity on the circular orbit is mu divided by a. And in particular, if you like to change back mu divided by r, r is the radius of the orbit. Okay. So v is constant. So this saying that as long as the r is constant, basically v is constant. So one now, this is a circular orbit. This is the Earth. Okay. So the satellites here, the satellites moving on the circular orbits with a constant speed at any moment. Okay. So that's the one here. And the same thing, the period. The period still using these formulas: 2 pi. R3 over mu. So the period is still the same, and right now r is constant. So t, this one can be estimated by that way. The second one is parabolic. For parabolic orbits, we pick up is this. So mechanical energy, the same thing, is v squared over 2 minus mu over r. Okay, that's the same for all kinds of the orbits. In particular for parabolic orbits, and in our definition, that corresponding is mechanical energy equal to 0. So this term is 0. And this term is always true for anywhere on the orbits. So right now we want to define special terms is in specific at the locations very infinite from whatever the coordinate system is. Here you see z equal to v squared over 2 minus sorry, let me repeat. Okay, so from here, basically this term will be gone. Okay, so therefore at there you can see V equal to 0 at R approaching to infinity. So that is a spatial properties is this. We simply define the parabolic orbit is in such a way is mechanical energy has this property when, for example, when this device or this object is very far away from whatever the coordinate system is, then its velocity simply becomes 0. Compared to hyperbolic, its mechanical energy is greater than 0. So here we can do the little bit same thing here. So energy is greater than 0. Again, specific energy, we can do the same thing here. 2 squared minus mu r. When we study r approaching to infinity, again, this term equal to 0. Compared to hyperbolic orbits, you can see V is greater than 0 at r approaching to infinity. So that is a difference between the hyperbolic and parabolic orbit. Parabolic orbits that has more energy than necessary to bring the device or satellites to infinity. Even if it go there, it won't stop, it still keep moving. But for parabolic, it just bring enough energy. It just have enough energy to bring the things to infinity. Once it get there, it stop. Okay, so that is the things here. Okay. And so that is the comparisons. And for this one, we have this is the first one, the second one. At any location R, we can have is this 0 equal to this one right now still in parabolic energy and V squared over 2 minus mu over R. At any location R, right now R is not constant. So here V we can describe is 2 mu over R. So at any locations, mu, the velocity equal to this. So for example, if this is the Earth, and this is the center of the Earth, okay, so here is the launching site here. Okay, so at the launching site, you want to launch not like normal, right now we're recording, I shouldn't say any words. Okay, so this is the rocket. If you wish, so right now for this case, you can see if this is the focus, so this is R. And if you wish to have this rocket to be launched and bring this rocket to infinity, deep of the space, what kind of the velocity you need to give to this one to make that happen? You can calculate based upon this one, right? If you wish to send this rocket or the satellites on the rocket to the infinity, to the very deep of space, then you have to go to parabolic orbit. Otherwise, otherwise, if your energy is less than 0, then eventually you wind up is the different size of the cyclic motion, right? So the only thing with the minimum required energy, sending the things to very far away, no returning ticket is go to here. So from here, you simply R equal to the radius of the Earth, right? You plug into here, you do the calculation, you can quickly determine the escape velocity. So here is ESC. Okay, so that is the escape velocity. That means to have anything to escape from the Earth or anything to escape from wherever the focus will be controlled. So in this one, once it is on, then I believe that will be something like this in certain one way where it's no return. Okay, so that is one, and this is the one more terminologies and provided to you. And again, you don't need to memorize, and cheat sheet will be have this one. But again, the concept is to simply have the things to obtain the energy enough to go to infinity. Of course, you can always get more energy like this one, and then As long as you can get thin, then you don't care how much energy left when go to infinity, then you can always give more, but okay. So that is for the orbit. Then we go to the next section is for practice the handout.